Please title these notes Limits to Notes, Algebraic Limits for Continuous and Piecewise Functions. By the end of this lecture, you should be able to use algebra to find limits when you don't have a graph, under specific circumstances, namely for continuous and for piecewise functions. So when we're working to find limits using algebra, we're still working with the same features that we were in limits 1, we just can't see them. So we're still going to have times when we're looking for the end behavior, what's happening as x approaches infinity, sometimes when we're approaching a vertical asymptote, sometimes at a jump discontinuity, sometimes at a continuous function where everything's just flowing real smoothly, sometimes at a removable discontinuity. So the way that we approach these is we really are always going to start with all of them by just plugging in the number that we're approaching for x and then see what happens. And what we get is going to tell us which of these features we have and what we would expect our answer to be. It's also going to tell us what methods we should use to solve it. So let's write this down. To determine the limit of a function algebraically, start by plugging in the number x approaches This will tell you what feature, and by that I mean vertical asymptote, jump discontinuity, so on and so forth, the curve has at that value. So when we plug in our number, I'm just going to go through the list of what the results tell us about what we have, and then I'll go through some examples. If the result is a finite number, so that's any number other than infinity, so pi is a finite number. 0 is -1, positive 297 million. Those are all finite numbers. It's just anything not infinity. The function is continuous at that value of x. So the number is the answer. This is true only when we're not working with piecewise functions. With piecewise functions, it's not guaranteed, but we'll talk about them in a little bit. Piecewise functions are just the ones that have the funky squiggly bracket, and so there are different equations for different values of x. Another thing that can happen, if the result is a non-zero number over 0, the function approaches a vertical asymptote like that right up there, and so that means our options are either positive infinity or negative infinity. Or it could be does not exist. That's if they don't match. If the result is 0 over 0, the function has a removable discontinuity. The limit will be a number. This, by the way, is called the indeterminate form. Basically, it's just icky. We have to do some more playing with it, and we'll see how to do that in a while. Then there are a couple of special cases. One is if x approaches infinity. We need special rules to quote-unquote plug in, because we can't really plug in infinity. What that means, though, with the positive or the negative infinity, it means that we're asking what happens as the curve goes off the edge of the graph to the left or to the right. And so it's either going to go up to positive infinity, down to negative infinity, or approach a horizontal asymptote. We're going to do more rules for this in another lesson. And finally, if there is a piecewise function so that's f of x equals, and then like one thing if x is less than a, and then another thing if x is greater than a, it's that kind of thing. Then there could be a jump or removable discontinuity if we are finding the limit as x approaches a. So if this number that we're finding the limit at is not the same as the one where we switch from one equation to the other equation, then we could still have some of these other situations going on, but we're only going to have that jump discontinuity at this switch. One thing I want to mention is that these are two special cases where these are going to affect what we do to put in the input. These three are based on what the output is. If we're able to plug in a finite number, what we get out. So these are situations where plugging in is hard. These three situations are based on we plugged in a number, look at what we got. Okay, let's go ahead and take a look at some of these examples. So let's say we're finding the limit as x approaches 0 of x squared. Well, the first thing we're going to try with these, unless we have either infinity here or one of the piecewise functions where we have to do something a little bit different. So we're just going to take this number, we're just going to plop it in here. Because the thing is that a lot of the time what we're dealing with is a continuous function, where whatever x squared is when x equals 0, I mean, that's the limit, that's also the value. So let's see if that works. 0 squared equals 0. This is a finite number. the function is continuous, at x equals 0, limit is 0. That's all there is to it. Let's say we have the limit as x approaches 1 of 1 over x minus 1. So what I'm going to do is I'm just going to start off by trying to plug in this 1 right here. So I'm going to do 1. It's going to give me 1 over 0. So this, looking at what I had over here, it's a non-zero number over 0, so we have a vertical asymptote. So that means the limit is either positive or negative infinity, or does not exist. We're going to go over, again, how to figure out which one of those it is. So that'll be in the next lesson. We could have the limit as x approaches 1 of x squared minus 1 over x minus 1. And so if we do that, if we just pop that 1 in both places, we've got 1 squared minus 1 over 1 minus 1. That's going to give us 0 over 0. That means, if we look back at our little rules, that is the indeterminate form. There's a removable discontinuity. That means the limit is a number. And then something like this, limit as x approaches infinity. I really don't even have to look at what I'm writing here. It could be anything. As soon as I see that, I know that we're in a situation, actually I shouldn't even put the arrow pointing there. I should really put it pointing to over here. Means we're going off the edge. The answer either positive and negative infinity or a horizontal asymptote. And finally, let's say we have the limit as x approaches 4 of f of x, and we're told that f of x equals 2 if x is less than 4 and equals 6x if x is greater than or equal to 4. Notice that these match, so that means there's a potential jump discontinuity. If we were evaluating this or finding the limit at x equals 3 and it wasn't the same number, then we wouldn't have a potential jump discontinuity. There might be something else going on. But it's only because these two match that we have to worry about that. So we're going to be looking at these over the next couple of lessons. For today, we're going to just start off with E and with A. We're going to be looking at finding limits when plugging in gives a finite number. So that happens both in this case and in the case of the piecewise functions. So just set these other three aside for a little bit. We'll come back to them in the next lesson. So here's a problem. Let's find the limit as x approaches 5 of x squared plus 1. So all we're going to do is we're going to take this 5, we're going to plug it in for x. 25 plus 1 is 26. That's a finite number. That's our answer. Done. Nothing more to it. That seems so easy. It went by way too quickly. Let's do another one. Limit x approaches 2. Let's do x plus 5 over x minus 3. So all I'm going to do, I'm going to plug that 2 in for x. Really is that easy. We're done. Where it gets more complicated is if we have this situation. Let's say there's a limit as x approaches 3 of f of x, and we know f of x is 3x plus 1 if x is less than 3, and it's x squared if x is greater than or equal to 3. Now I notice that this matches those two, so we have a potential jump discontinuity. What that means, here, I'm going to bring these little arrows over here. What that means is it means we need to find the limit from both sides to see if it matches up. Because here's what could be going on. We could have a situation like this, where we've got one function here, and it's bad. That could be what's going on. Or we could have something, because there's a discontinuity, there's no overall limit. Notice that here we're looking for the overall limit. Or we could have a situation where it's something like this. Let's say it's going off like this, and we've got this other one coming up like here. But it just so happens that they have a point in common. This would mean that there is an overall limit because the left limit and the right limit are the same. Here there wouldn't be an overall limit. So if we want to find the overall limit of this one right here, I'm just going to point out, find overall limit. Then we need to find the left limit and the right limit and put them together. So if they're the same, the limit as x approaches 3 with no little plus or minus of f of x is the number they both equal. If not, if they don't match, limit as x approaches 3 of f of x does not exist. So let's find each of these pieces. This is still the same problem, number 3. So we need to find the limit of f of x as x approaches 3 from the left, limit as x approaches 3 from the right, and then we're going to have to compare those to get the overall limit. The problem we encounter, I rewrote what f of x was up here, is that I know that I want to plug in this 3, but I have two different equations. The question is which one I'm going to plug it in for. And the thing to remember about piecewise functions is that what's really going on is that we've got our xy coordinates. We're going to graph it. 3x plus 1, that's a line. X squared, that's a parabola. But we only want to graph this 3x plus 1 when x is less than 3. So that means that on this side of 3, less than left, we've got this function right here. It's over here on the left. Whereas when x is greater than 3, over here on the right, then that means that f of x equals x squared. So what we have to do, let's see, this is f of x equals f of x equals x squared. So I have to say, okay, if I'm approaching right over here, if I'm approaching 3 from the left, then I want to use the equation that's on the left hand, that's on the less than side. Notice these are always written from left to right when they're being written. So that means that this is going to be the same as the limit as x approaches 3 from the left of 3x minus 1. Because that's the one that's to the left of 3. So in that case, all I'm going to do is I'm going to take that 3, I'm going to plug it in for x. 3 times 3 is 9, minus 1 is, oops, it was plus 1, my bad. Plus 1 is 10. There's my left-hand limit. On the other hand, here I'm working with as we approach 3 from the right. So I want to use the function that's on the right. I want to use the function that's for greater than 3. So that means we're going to have the limit as x approaches 3 of x squared. And I'm still just going to plug that 3 right in there. Notice the limit as x approaches 3 from the left is not the same as the limit of f of x as x approaches 3 from the right. So the overall limit does not exist. Those are really the main ideas. We're going to just do a couple more examples with them, and then we'll be done with this lecture. Okay, so number 4, let's find the limit as x approaches 4 of g of x. And g of x, also a piecewise function, is going to be 2x if x is less than or equal to 4. It's going to be x plus 4 if x is greater than 4. So what that means, it means that if we were going to graph this function, or splitting it off at 4, when x is less than 4, so all the way over here we have g of x equals 2x, and when x is greater than 4, off to the right here, we have g of x equals x plus 4. So because we have a piecewise function, we could have a jump discontinuity. So we have to check both the limit as we approach from the left. And if we do that, we're going to use the left side function, so that's 2x. So that's going to be 2 times 4 equals 8. And we also have to check the limit of g of x as x approaches 4 from the right. So we use the function that's on the right-hand side of 4, that's x plus 4. Notice in this case, the limit as x approaches 4 from the left is the same as the limit as x approaches 4 from the right, and they both equal 8. So the limit overall as x approaches 4 is 8. Sometimes these problems can be a little bit sneaky, like so many problems can be. Let's say we have this one. This is the limit as x approaches 2 of h of x. And we're going to say h of x is x squared plus 1 if x is less than 3, and it's negative 5x if x is greater than 3. Notice that when x equals 3, there is in fact no value at all. We have no equal signs here. We could have had something in the middle that says, okay, you know, when x equals 3, there's this particular number. But But all we care about with the limit is what we're approaching. So we actually don't care about what would happen if x equaled 3. And in this case, we really don't care about what happens when x equals 3 because we're evaluating the limit at x equals 2. So what makes this problem sneaky is that if we go to draw it, we've got h of x equals x squared plus 1 on one side. We've got h of x equals negative 5x on the other side. But when we go to do our left and our right limit, the number that we're looking at is actually 2. It's actually right there. It's wholly inside the domain that has this one. It's only when we are trying to find the limit at this number right here that we have to do the left and the right limit. Because on one side of 3, it's one equation, and on the other side of 3, it's the other equation. But here at 2, at 1.9 and at 2.1 on both sides of 2, it's still the same equation. So for this, all this is going to be of that pink one. So we can just plug that 2 right in, and that's our answer. We don't need to use both equations because the equations switch at x equals 3, and we're finding the limit at x equals 2 instead. Sometimes, like I was alluding to up here, we have a situation where we're saying, let's say, the limit of k of x as x approaches 4. And let's say that k of x actually has 3 different equations. Let's say one is 3x if x is less than 4, 2 if x equals 4, and 7 if x is greater than 4. Let's find the limit for k of x as x approaches 4. So what would happen if we were to graph this? So we've got this switch at 4. And on one side, less than 4 to the left, k of x equals 3x. Whoops, let's try that. There we go. K of x equals 3x. On the other side, when x is greater than 4, k of x equals 7. And then exactly right here, when x exactly equals 4, there's a little dot at 2. I'm just going to underline those in the colors. There we go. Now, the really key important thing we don't care. When x equals 4, we don't care what's happening. So we can really just ignore this one right here, because we're talking about the limits. We're talking about its hopes and dreams and aspirations. As it's coming from this side, it wants to be on the line 3x. It wants to be on the line that's going through right about like this. You don't have to be able to draw this, but I just want to show you what's going on. It's going like that. And let's see, when 4, it's going to be at 12, okay. And over here on this side, it wants to be on this line. It isn't right here because it's not when x is greater than or equal to 4, just when it's greater than. But it wants to be on that line right there. So when we're looking for the limits, we're looking for, as we are approaching from the left, what does it want to be? As we are approaching from the right, what does it want to be? What it actually is, we don't care. This dot could be anywhere. So one very common error with problems like this is that students will go, okay, I want the limit as x approaches 4, so I say when x equals 4, f of x is 2, so the answer is 2. No, it's not. When we're doing this, when we have an overall limit, we have to do limit as x approaches 4 from the left, limit as x approaches 4 from the right. The only reason we didn't do that up here was because the number that we were finding the limit at was not the same as these numbers here. Here, the number we're finding the limit at is the same as these numbers here. We have to do both of them. So we're coming from the left, we're going to use the left equation. So that's going to be 3 times 4 gives us 12. This one we're going to use the right equation. It's just saying that it's 7. And notice here there is no x for us to plug in, so the answer is just 7. 7, no matter what x is, still 7. So when we're looking for the overall limit as x approaches 4, k of x, because the left limit does not equal so the overall limit does not exist. The final problem looks just a tiny bit different. Limit as x approaches 5, j of x, and j of x is going to equal 2 if x equals 5, and it's going to equal negative, negative x plus 8 if x does not equal 5. So what that means in terms of what this looks like is that when x equals 5, we have a dot here at 2. But not equal to 5 both means on the left and on the right. So over here, j of x equals negative x plus 8, and over here, j of x equals negative x plus 8. If I were going to go and graph this, it would look something like this. There's our negative x plus 8. It's holding true everywhere except for this one value where we have this removable discontinuity. The dot has been taken out and it's been moved down. So in this case, there's really only one equation that we're working with because we do not care. X equals means don't care. This is about hopes and ideals, not what's actually happening. So that means that the limit here, we're going to be, I'm going to run out of room, so I'm going to put it down here. We're going to be finding the limit as x approaches 5 of this negative x plus 8. And the only reason that I'm not writing two equations like we did up here is because the left equation and the right equation are exactly the same. Just like up here, relative to the number 2, the left equation and the right equation are the same. Yeah, there's a different one once we get past 3, but we don't care about 3. We only care about what's happening right around 2. So here, if you are at all confused, you can absolutely do the left-hand limit and the right-hand limit. They are going to be the same because there's only one equation, and if we plug in 5 into negative x plus 8 for the left-hand equation, and we plug in 5 to the negative x plus 8 for the right-hand equation, you get the same thing because they're the same equation. So that would be negative 5 plus 8 equals 3. That concludes Limits 2 notes.